Good morning, one and all. Uh, Now let's move on to the another topic in the feedback amplifier module 3 part B in the analog electronic circuits BEE 303. Okay, the topic is today's topic is classification of basic amplifiers. Classification of basic amplifiers. Okay, uh, in the classification of basic amplifiers, we have four types. As of we discussed in the previous class, first one is voltage amplifier, second one is current amplifier, third one is trans resistance amplifier, fourth one is transconductance amplifier. We know the basic equation for voltage amplifier AV is nothing but voltage gain is equal to output voltage divided by input voltage. AI current gain is nothing but I naught divided by II. And trans resistance is nothing but Rm is equal to V naught divided by VI Ohm's law. V naught divided by output voltage divided by input current. Here we are going to calculate trans resistance. Okay, that is nothing but trans resistance amplifier gain Rm is equal to output divided by input. What is there? It's the Ohm's law. We need to apply Ohm's law also. Output divided by input. In the output voltage, in the input current. Okay, that's we need to take down. Transconductance is the vice versa of our trans resistance or analogy of our trans resistance. So GM is equal to output current divided by input voltage. Reverse order compared to our trans resistance. Okay, I hope all of you understand about this classification. Now, let's we go to the derivation part. We need to find out the equation for VI and V naught in order to find out the voltage gain. So first we need to take down AV is equal to V naught divided by VI. That is nothing but voltage amplifier. Voltage amplifier. Students, here uh, voltage amplifier. First, we need to consider this equation. This equation is very, very important. We need to consider this equation and we need to remember the block diagram. What is there in the block diagram? Source signal, mixer, basic amplifier, sampling circuit, and then finally load, and then feedback circuit. These are all the things we should know. And then feedback is nothing but beta. Normal gain, gain of the amplifier is nothing but A. Feedback gain AF. AF method beta both are same. Okay, we should know those basic. Okay, output variable here, output variable is V naught, input variable is VI, input voltage, output voltage. So both are in the output also voltage, in the input also voltage. So we can go for Thevenin's theorem. Thevenin's theorem. So Thevenin's theorem we can apply for this one. How to represent Thevenin's theorem? We need to apply Thevenin's theorem for input, and we need to apply Thevenin's theorem for output also. So we need to apply Thevenin's theorem. How to apply Thevenin's theorem? We need to write down the source Vs is Vs and series resistance, source resistance Rs and input resistance Ri in the series format. Okay, and then AVVI, that is nothing but a V naught is equal to, we know the equation for AV is equal to V naught divided by VI. What is the equation for V naught? V naught is equal to, this is nothing but a V naught. V naught. How to represent this V naught? V naught is equal to, with the help of this equation, we can solve this one. V naught is equal to AB into VI. This equation we should write in the output side here. Okay, and then R naught. Here Ri, here Rs, here R naught, and here Ri, here load resistance RL. We need to mention this V naught. This is input Thevenin circuit. This is output Thevenin circuit. RA is nothing but amplifier input circuit, input resistance. RS is nothing but source resistance. R naught is nothing but output resistance. RL is nothing but load resistance. Okay. Now let's move on to the next part. Here we need to apply KVL for the input flow. How to apply the voltage divider rule? What do you mean by voltage divider rule? Here we need to find out VI. Okay, VI. How to apply voltage divider rule? All of you understand. VI. Okay, I'm going to rub the board. Okay, first we need to understand what you mean by voltage divider rule. Here, we need to apply voltage divider rule in order to find out the VI. How to apply voltage divider rule? Very simple, students. I want VI. I want VI. The voltage across RI. Okay, so I want VI. That should you write in the LHS is equal to, in the RHS right hand side, we need to write what is the total input voltage here? Vs. You need to write out here. Vs into across resistance, which voltage we find out, we need to find out that resistance, we need to take the Ri divided by sum of resistance. What are all those resistance are there in the series format? Rs plus Rs plus Ri. So this is how we need to write the voltage divider rule. This is how we need to implement the voltage divider rule for input circuit. I hope all of you understand. Here we need to consider what is a single term here in the numerator or denominator. Here numerator also have Ri, denominator also Ri. So we know we can cancel directly. But here Rs is there. So Ri is double greater than Rs. Ri is double greater than Rs. I hope all of you understand. Those terms in general term or in simple language, you can remember like this. Those terms are there in a single format, in only in the denominator. That is the value should be less. Okay, so that's why Ri is greater than, double greater than Rs. In that time, we can neglect Rs. We can keep it Ri only. We can keep Ri only in the numerator and denominator. In that time, Ri will going to get cancelled. Vi is equal to Vs. Vi is equal to Vs. This is how we can remember. Okay. Now I'm going to represent the resistance values here for an ideal voltage amplifier without any losses. In that time, Ri is a double greater than, means we can take infinite value. Infinite value for a practical voltage amplifier, design should be such that Ri should be greater value we should be take. We can't tell like that infinite value I will go to select for Ri. So we need to take some maximum value of Ri. Okay, now I move on to the second part. We need to find out V naught. So that's why I'm going to apply voltage divider rule for output circuit. How to apply voltage divider rule for output circuit? I'm going to explain you guys. Okay, how to apply voltage divider? I'm going to rub the board now. I'm going to rub the board. Okay, how to apply voltage divider rule? Just apply voltage divider rule for output circuit. This circuit, for this circuit. How to apply? Students, all of you listen. All of you listen. How to apply voltage divider rule? How to apply? Okay, I want V naught. V naught is equal to, okay, I will write here. V naught is equal to, V naught is equal to total input voltage AV, AV, VI, VI into what? Into which resistance across we are going to check the V naught. So that's why we need to take that resistance RL divided by sum of resistance, that is nothing but R naught plus RL, R naught plus RL. Okay, this is how we need to apply the voltage divider rule. Okay, that I am already written here. Please check it out. V naught is equal to same equation. V naught is equal to V naught is equal to V naught is equal to AV. V naught is equal to AV. V naught is equal to AV VI RL divided by R naught plus RL, which is the one single term here, R naught. So RL is double greater than R naught. In that time, I'm going to neglect this R naught and I'm going to consider only RL. In that time, when we consider only RL, in that time, RL will going to get cancelled. So AV VI will going to remain. V naught is equal to AV VI. So what is the condition here for an ideal voltage amplifier? Just concentrate on R naught. In the input side, input resistance we need to concentrate. In the output side, output resistance we need to concentrate. R naught for an ideal voltage amplifier, R naught is 0. We need not to worry about RL. Maximum or ugly, minimum ugly. So we don't worry about RL. We just concentrate on RI and R naught. So here R naught is 0. Ideally, for practically, how we need to select minimum value or the small value we need to take for R naught. So next we move on to the current amplifier. You can analyze by your own, but here the small thing is we need to apply the Norton's theorem. How to apply Norton's theorem? I'm going to explain now. Okay, what is the current amplifier formula? Current amplifier formula is nothing but AI is equal to I naught divided by II. Output signal current, our input signal current, both are current. So we need to apply Norton's theorem for I naught, Norton's theorem for II. How to apply Norton's theorem? The counter what is the directly opposite to the Thevenin's theorem. Thevenin's theorem, all the resistance are in series. Here, both the resistance are in parallel. In the output side also, in the input side also. Why? Because we apply both current Norton's theorem for both input and output. So IS parallel RS parallel RI. Here also, here how we can get this equation? I naught is equal to AI into II, AI into II. I naught is equal to AI into II. R naught in parallel, RL in parallel. Input circuit, Norton circuit, output Norton circuit, output Norton circuit. Here what we need to apply? Here we need to apply current divider rule. In the when we apply Thevenin's theorem, we need to apply current voltage divider rule. When we apply Norton's theorem, we need to apply current divider rule. How to apply current divider rule, students? All of you should know the basics of how to apply current divider rule. It's very easy, but if you don't understand, it's very complicated. Even I also face a lot of struggling to understand these things. So that's why there is no issue in the understanding. Simultaneously, you need to put some effort and try to understand the things to clear the subject. Simultaneously, do the practice and remember these questions are maybe useful for your placement for core companies like Tesla Semiconductor, Tata Elxsi. Most of the electronics based company, they will going to ask these very basic questions. How to explain? You can explain voltage amplifier, current amplifier, transfer resistance amplifier, transconductance amplifier. Those things are very, very important. At least we should know the basics, at least types, at least one analysis. That thing we should know. Okay. Okay. How to apply voltage divider rule, how to apply current divider rule. These are all the things we should know. Not Norton's theorem statement, Thevenin's theorem statement. These are all the things we should know. Okay. Apply current division rule on the input side. How to apply current divider rule? I want here II. How to apply current divider rule? II in the LHS is equal to total current, same like Thevenin's theorem, but here we need to take opposite resistance, RS divided by RS plus RI. Here, what is the single term? RI. So, RS double greater than RI. In that time, RI we should cancel, neglect, and RS, what will going to remain? RS. So, RS will going to get cancelled. So, I is equal to IS. So here what will going to happen? We need to concentrate on only Ri. Ri is 0 ideally, but it's not possible to take 0 in the practical condition. So that's why we need to take small value that I wrote in the last. Okay. Now let's concentrate on current divider rule. We need to apply in the input side. How to apply current divider rule for input side? So just concentrate on here. How to apply current divider rule for input side? Very simple. Very simple. Okay. Here I want I naught. Here I want I naught. So that's why I naught is equal to AV, AV, II, AV, II into what is the opposite resistance, students? R naught divided by R naught plus RL, R naught plus RL, R naught plus RL. Here, what is the single term? So, RL is the single term. So ಅದಕ್ಕೋಸ್ಕರ R naught double greater than RL. R naught double greater than RL. So in that time, we need to neglect this RL, consider only R naught. In that time, R naught will going to get cancelled. This is 0. So what will going to remain? I naught is equal to AV into II. AV into II. Let's check. May I write or wrong? Let's check in the notes. Okay. Yes. Yes. Okay, I'm correct here. I'm correct. Okay. So what is the condition here? Very simple. For input circuit, for an ideal current amplifier, Ri is 0, R naught is infinite. For input circuit, Ri is 0. In the R naught here, infinite. For practical case, we need to take Ri, we need not to take Ri is equal to, we're not able to take 0 ideally. So practically we need to take Ri small. Okay, and then R naught is very large. R naught is very large. Instead of infinite, we need to take in the practical very large. Okay, so now let's move on to the next topic. So that is nothing but our transconductance. Very, very, very important. Now we need to understand transconductance. How to understand this one? Very simple. Very simple. First, I'm going to erase the board. Erase the board. Now, GM, what is the transconductance equation? GM is equal to I naught divided by VI. In the output term, current is there. In the input side, voltage is there. So for input voltage, we need to apply Thevenin's theorem. For current, Norton's theorem, as per our early understanding. So how to extract I naught? I naught is equal to GMVI. For input side, we need to apply Thevenin's theorem. How to apply Thevenin's theorem? As per we can refer previous circuit, voltage amplifier circuit, VS, RS, RI. Same, everything is remaining same. For Norton's theorem, how to apply Norton's theorem? We know the equation. I naught is equal to GMVI. GMVI, R naught, RL is parallel. So next, apply voltage divider rule for why? Because it is a Thevenin's theorem. So apply voltage divider rule. Apply voltage divider rule for input circuit. What will going to come? What will going to come? Very simple. Very simple. So I want VI. VI is equal to VS across RI divided by RI plus RS. So one term is RS. Lesser. We should take less. So RI is double greater than RS. In that time, RS infinite. In that time, what will going to happen? RS will going to be 0. RI will going to get cancelled. VI is equal to VS. So next, I'm going to take here what? Here Ri is infinite. So output circuit we need to apply current divider rule. Why? Because I apply Norton's theorem. Norton's theorem. So what is Norton's theorem? Here I naught is equal to GMVI into R naught divided by RL plus R naught. I hope all of you understand. I'm not going to explain in depth. Okay, just I will explain for this only. From the next circuit, you need to just understand by yourself. Okay. Now I am going to apply Norton's theorem. I naught I want I naught. I naught is equal to what, students? I naught is equal to I want total input or current is equal to GMVI, 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 GMVI. I'm going to write another one second. GM. I naught is equal to GMVI, GMVI, GMVI into opposite resistance R naught divided by R naught plus R naught plus RL, R naught plus RL. Okay. For an ideal transconductance amplifier, Ri is equal to R infinite, R naught is equal to infinite. For practical, we should take higher values. Okay. Next, for trans resistance. Trans resistance also Rm is equal to V naught divided by II. V naught we should apply Thevenin's theorem. For II we need to apply Norton's theorem. Circuit look like this. We need to apply for input circuit. We need to apply for current divider rule, and for output circuit we need to apply voltage divider rule. And this is the equation. II is equal to Is into Rs divided by R1 plus Rs. So here RS will going to get cancelled. R1 we should take Ri we should take 0. I is equal to Is. Apply voltage divider rule for output circuit because we need to apply, we already applied Thevenin's theorem. So V naught is equal to Rm, Ri will going to come. So I hope all of you clear. If this is the conclusion. Okay, parameters, voltage amplifier, current amplifier, transconductance amplifier, transfer resistance amplifier, input resistance for voltage amplifier infinite, input resistance for current amplifier 0, for input resistance for transconductance 0. I think check it out. Check it out. Transfer resistance 0, output resistance for voltage amplifier 0, output resistance for current amplifier infinite, output resistance for transconductance infinite, transfer resistance, output resistance is 0, transfer gain, you know all the transfer gain. Okay, thank you.